An electron is moving vertically up with a speed of 3 times 10 to the 7th meters per second. We'd like to find the direction and magnitude of the magnetic field that the electron creates at points A, B, C, and D. All these points are at equal distance from the electron, which is equal to 1.5 times 10 to the negative 6 meters. So we'll just use the formula for magnetic field created by a point charge. Mu 0 divided by 4 pi times qv sine theta divided by r squared. Q is the charge of the particle, v is the speed of the particle. Theta is the angle between the particle's velocity vector and vector r hat. Now, what is vector r hat? It's the vector, unit vector, that points from the position of the particle towards the point of interest. So for instance, this is r hat for point A. Let me label it as r hat sub A. On the other hand, r hats for point D will look like this. So r hat sub D is this one. Because this is a unit vector, its magnitude is just 1. So what we really care about is its direction. And so what's the angle theta then? For point A, the angle theta is this one right here. So this is theta A, which is 30 degrees. How about theta for point D? The velocity vector is pointing vertically up and r hat D is pointing vertically down. So the angle between the two is this whole thing, theta D, which is 180 degrees. So this is theta sub D. Similarly, theta B is equal to 150 degrees. The angle all the way from the velocity vector to this dashed line, this is my r hat for point B, and theta C is 90 degrees. This angle right here is theta C, basically, all the way from the velocity vector's direction to the dashed line that points to point C, which is the direction of r hat sub C. Let's apply our formula. The only thing that's different for each point is the angle theta. So I evaluated the numerical parts except sine theta. So I get B equals 2.1 times 10 to negative 7 Tesla times sine theta. So now let's go ahead and calculate the magnitude of the magnetic field for each point separately. The angle for point A is 30 degrees, so we multiply 2.1 times 10 to negative 7 Tesla by sine 30, and we get 1.1 times 10 to negative 7 Tesla for the magnitude of the magnetic field at point A. For point B, we get the same numerical result because sine of 30 degrees is the same as the sine of 150 degrees, so that's the same magnitude of magnetic field. At point C, on the other hand, we get the greatest value of the magnetic field because sine 90 degrees is equal to 1. So the magnetic field magnitude at point C is equal to 2.1 times 10 to negative 7 Tesla. And as I mentioned earlier, because point D is at an angle of 180 degrees, sine 180 is 0, and the magnetic field at point D is 0. Now, how about the direction of the magnetic field vector at each point? We apply the right-hand rule. We are going to do V cross R hat for each point. Extend your right hand, in the direction of the velocity vector, which is pointing up, and then curl your fingers in the direction of R hat A, which is pointing towards the upper right corner. So basically, you're curling your fingers towards right. Your thumb is pointing into the page. Now, this would have been the direction of the magnetic field if we had a positively charged particle. Because this is a negatively charged particle, the direction is the opposite of that. So the magnetic field vector at point A points out of the page. For points C and B, The way we apply the right hand rule is the same. We extend our right hand up and then we curl our fingers to the right. The only thing is that the angles are larger for the r hat vectors for C and B, but the way we curl our fingers is the same. So then we end up with our thumb pointing into the page, but because this is a negatively charged particle, we flip the direction, and out of the page is the direction of the magnetic field at points C and B as well.